We are to our keynote address by Carver Mead, and doggone it, my internet went down, and I don't have my intro form on there, but I can get it right here. Bear with me. And my phone is frozen. Cannot activate cellular network either. He needs no introduction. Who said that? All right. Well, thank you for coming on up, and would you go ahead and do the honors of introducing yourself since I don't have the sheets in front of me. Thank you. This is the man who invented Moore's Law. That's what I wanted to get to. You don't have any bigger thinker in technology than this guy right here. It is truly my honor to unfortunately mess up this introduction, but please, take over.
Well, this telecosm I've been fortunate to go to almost every year, George, and it's always been a joy. And telecosm is about information. And information's a very funny thing. In a way, information and money are very similar. In fact, George just wrote a book about that, or is writing one. You think of information as sort of a disembodied thing, like it exists without any physical form. But after you think about it a little bit, it can't exist without a physical form. If it's going to be there when you need it, it has to be stored. If it's going to be there where you want it, it has to be transported. And if it's going to do anything, it has to be processed. And any of those actions require physical stuff to do it. So although we think about information as sort of a disembodied thing, it's totally dependent on physical substrates to do anything. And that's true of information. It's true of money. You think of money, it's just a number in a ledger somewhere. But when you go to buy a house or a new car or something, it better be there to do that. And the same thing with our life information. Has to be in the DNA, or we wouldn't be here. As someone that's spent my life working on the physical substrate for information, you get some insights that aren't as easy to get if you're just working with what we call software. I'd like to just share some of those with you today. We've heard a lot about the big revolutions that are taking place because of the information substrate that we've built carefully and painfully over the last 30 or 40 years. And when we were down in the trenches doing the next step of figuring out why we couldn't make transistors smaller and why we couldn't make the networks go faster and why we could only get a few kilometers of signals over fiber optic. And we're struggling with all those issues, which of course we're still struggling with, but we've struggled a long way, as Andy told you. One of the things you find out very early on, I was fortunate to find out in the late 50s, early 60s, is that when you're trying to actually push the technology forward, the stuff that's in the textbooks doesn't really help very much. And so you have to go and just figure it out yourself. And that was true for all of us who were doing that. We all learned the stuff out of the textbooks, and then we tried to rely on that to get things to work, and you can't get things to work that way. So we had to figure it out our own way. And in the process, there's a tremendous number of people who have figured stuff out their own way that simply has not made it back into the textbooks. I'll just share a little of that with you today. Any of the technologies that are involved in our information substrate, when we were working on them close up, we ran right smack dab into the fact that these things weren't like mechanical systems. They weren't like cars and wheelbarrows and shovels. That's true of all the technologies involved in information. They were quantum systems. And quantum systems simply don't work like the mechanical systems we got a feeling for when we were kids. So what do I mean by a quantum system? Well, there are two things that characterize a quantum system. A thing like an electron. The first is that there are little bits of matter. Matter is what we all know everything's made out of. But they don't behave like just smaller and smaller grains of sand. We all got raised with what I call the particle picture. That these things, atoms, were just real small grains of sand, and the electron and the proton and the atom were just smaller than that. But they were these little points. And they're just not like that. What they're more like is a wave, like a radio wave or a light wave. They behave more like that. And you say, well, it can't be like that because a wave just spreads out and gets bigger and bigger and bigger. Well, that's what electrons do if you leave them alone. Even a single electron spread out. The reason that matter seems to have little particles in it is this thing we call electric charge, where electrons have a negative charge and the protons have a positive charge. And we were all taught as kids that opposite charges attract each other. So the protons go and pair up with electrons, and when they do that, they make a little bound state. And that's an atom. And of course, you can group together more protons and neutrons and more electrons and make more complicated atoms. And that's where the little particulate nature of matter starts. But down at the bottom, these things are waves. Take some getting used to. The second thing that is unfamiliar about the quantum world is the bidirectional nature of time. That sounds really weird. Everybody knows that time runs one direction. Well, how do we know that? Well, it sure does for us. Why does it do that for us? Well, time comes about in our ordinary experience from thermodynamics. Life in general lives deep in a thermal world. The energies we deal with are all measured in terms of the thermal energy. And any system that works that way, it's the entropy, the disorder of the thermal system that gives time its one-way direction. And for that reason, of course, you're not going to do time travel with people in it and that sort of thing. But something that has been misrepresented as a form of time travel happens in the quantum world. And what that is when you've all heard about light quanta, photons. And they've been pictured as little bullets of energy because we're used to particles and we're used to bullets and we're used to seeing things go with time. So when one atom gives up energy, it's absorbed by another atom. We think of this little bullet of energy in the field, which goes out and grabs the other atom. That's not what happens. People have tried to overlay our understanding of time on the quantum world. And when you do that, you say, oh, I'm an atom. I have to get rid of some energy. I'll put it in the field. And then the field will convey it all the way out till it finds the place it wants to land. And then it will cause a quantum jump. And the other atom will get the energy. And meanwhile, the energy was in the field. Well, I won't bore you with details, but if you follow your nose and just do that, you run into the biggest disconnect we've ever had in science. Because if you put the energy in the field, you find that even when you don't put it there, the field has its own writhing going on inside of it. And that writhing that would be going on in the field all by itself is more energy than you can possibly have in our universe and have it the way we observe it by a factor of 10 to the power 120. It's the biggest disconnect we've ever had in science. So, what do scientists do about it? They ignore it.
Like any good investor.
Like any good investor, yes. Well, that brings us to the next revolution. How could it possibly be ignored? Well, it's the same thing that happens in all fields. As science grew up, it grew into a set of specialties. And the people that do one specialty don't cross over very much into the other specialty. And the people who worried about the universe were people that worried about gravitation, the way big massive objects like planets and stars and nebula interact with each other. The people that worried about the field were people in particle physics, and they worried about accelerators and Higgs bosons and things like that. Just in the last decade or so, we've had these people trying to put together a picture that encompasses both of these disciplines. And it simply doesn't work by a factor of 10 to the power 120. Andy thought he had big factors. Andy, you haven't seen anything yet. So the disconnect we have in science today is profound, unaddressed, and desperately needs to be looked at. Once one thinks about it from the quantum point of view that I mentioned, it doesn't seem so hard. A number of people down through history have seen a way to stay out of the mess, but their thinking has not yet been incorporated into the mainstream of physics. The two things I mentioned, the fact that matter down at base is a wave, and that the interaction between bits of matter doesn't happen by throwing a little bullet or by putting the energy into the field. It actually happens by a very special kind of interaction between one element of matter and the other. And that interaction is best thought of as a transaction. It's a transaction that goes over space and time together. So a little homespun way of thinking about it is, this atom has some energy it wants to get rid of. In order to get rid of it, it has to make a trade. It has to find a customer who's willing to buy its energy. And that customer can be anywhere out in the universe as long as they're connected by what could be a light ray. And then what happens is the source of the energy sends out an offer, and the recipient sends back an acceptance. The difference between that and what we do in common life is the offer goes out forward in time. The acceptance comes back backwards in time. So both the source of the energy and the recipient of the energy experience the transaction in their own time. It takes some getting used to, but it's by far the most intuitive explanation for many of these very weird quantum phenomena that get featured in the popular press. Once you've grokked the situation with that mental model, which takes some stretching of your mind, you can see what Ernst Mach was talking about a couple of hundred years ago when he said, you know, nothing can have an inertia by itself. And Einstein was a big proponent of Mach's approach. The only way you know if something's moving is if it's moving relative to the rest of the stuff in the universe. And how does it know if it's moving with respect to the universe? Well, matter is all quantum at the bottom. So if we understand how one quantum element of matter interacts with another quantum element of matter, we can imagine how what we experience here and now depends on everything we can be connected to with a light ray, both in the past and in the future. It's a big idea. It stretches our mind. above all, it's a thought we could not have had until the present. If you think about it, we're never able to imagine anything that's very, very far from what we've experienced. And it's only in the last couple of decades that we are literally, by the technology we've talked about today, connected to nearly every human being on Earth. So we're just now experiencing something that puts us in a position to imagine a much, much bigger connectivity than we've ever imagined before. So we can imagine that the inertia of a baseball comes from its connection by gravitation with all the rest of the matter in the universe. We could never imagine that before. We weren't close enough to an experience that was even remotely like that. Technology has given us that experience, and it's given us the opportunity to have a much, much bigger view of the universe as we look out at it. And what's bound to happen is that science itself will have a revolution just like technology has. Thanks.
Stick around.